Just 1, 2, 3. Good morning, everybody. How's everybody today? All right, simmer down, simmer down. Sideways thumb? Yeah. Well, at least it's a Friday, right? Yeah. So, I had a question from one of your esteemed colleagues this morning. Are the TAs on strike? No, not yet anyway. I just would like to explain this process to you because it's come up and it's of interest and possible consequence. So, we were dealing with a similar situation over the summer. Thank you, by the way, for the generous loaning of your lightsaber. I'll be nicer to this one than the one that I broke. So with respect to the union, you may, of course, you probably know that both sessional professors such as myself, postdoctorate fellows, and TAs/RAs, by the way, and RA is definitely a thing you might want to shoot for as an undergraduate. It stands for research assistant. Basically, you get hired on to help with lab work. I don't hire any RAs because I'm not prof. All of these people are unionized. They occasionally have to renegotiate their contracts, and normally every single time they do, there's a threat of a strike. Whether or not that strike actually comes into existence is an entirely different matter. The thing that happened recently is that the TAs voted whether or not they are willing to go on strike should negotiations fail. That was the purpose of the strike vote. It's not, we vote to strike, therefore the strike is happening Monday. That's not the situation we're in, okay? The purpose of the strike vote is essentially, it's a further negotiation tactic that the union uses in its negotiations with the university. It's actually the case that the higher the percentage is on the strike vote, the less likely a strike is. In this case, we have a 90% of union members voting in favor of the strike. So, in my estimation, that would make actually having a strike much less likely than if it were in like the 60s or the 70s range. Basically, the employer takes this number as an indication of how much trouble they'll make if they actually do go on strike, or how long that strike will last should the strike actually happen. A strong strike vote, a strong strike mandate puts the union in a much stronger negotiating position, which most likely results in no strike rather than there being a strike. So, okay, so what if negotiations fail anyway and there is a strike? My general impression is that without the TAs, this whole institution grinds to a halt. My impression of how things will probably go is that classes will be suspended in the case of a general TA strike. God knows how long that would last. I've been in the middle of strikes before, and even a 3 or 4 week strike, pushes classes into January, which is terrible for all people involved. In general, if the union is serious about going on strike, again, that reduces the probability that they actually will. So don't panic. Even though they held the vote and voted to strike, that doesn't mean that we are on strike. You should still go to your tutorials today. In general, a good course of action is always to proceed as normal with a stiff upper lip until something actually happens. So that's the situation we're in with respect to that. Any questions? Okay. So there you go. Trade unionism at work. So, We've just got a couple of topics left to polish off in this topic, and then we'll talk about some complicated stuff. Some stuff that's really going to bake your noodles. So, last time we've been talking about functions and recursions, sort of more generally for quite some time now. We just have a few more details to polish off about functions, and then we'll be clear of this subject. We're going to discuss how functions might be used as objects. So, in general, one of the features that you may have noticed from your study of the Haskell programming language is that functions are first-class members of that programming language. What do I mean by that? It means that functions can be passed as arguments to functions, right? Haskell more or less considers everything a function. Even things like integer literals are considered functions that take 0 arguments. So it's a functional language. So why is this relevant to Python? Well, Python and some other object-oriented languages have drawn some inspiration, shall we say, from the functional paradigm. That's like, there's like, I forget the name, but there's like some supervillain who like kills superheroes, takes their power, and adds them to themselves. Oh wait, it's Mega Man. There we go. Mega Man does that. Yeah, Mega Man is the villain, by the way, in the Mega Man games. I don't know if you knew that. This is basically the approach that many of these sort of popular object-oriented languages take. They claim the title of multi-paradigm languages, despite being, fundamentally unsuited to such a title. But anyway, so Python has borrowed a few concepts from the functional paradigm, which hopefully everybody in this room has at least a small amount of familiarity with because of your current enrollment in 1JC3. So, we can pass functions to other functions as arguments in Python. So, one thing that you've probably used in Haskell so far is the map function, right? Yeah. This is your implementation of map as it exists in Python. Of course, it will only map to iterable objects, but in some senses it's more general than Haskell, because this will map over sets and dictionaries and other sort of strange occurrences, as well as your regular lists and tuples and strings and such things. So, for I in range 0 to the length of L, L at I, well, anything that you can access via numeric indexing in this particular example. If we were doing it differently, it would be different. Anyway, F applied to this element is reassigned back to the element. This requires that F be a function, right? It requires something callable. So you can pass callable things into functions. Right? This is, if you remember way back to the first opening weeks of September, the first code example that we ever did in this class contained such a thing. We passed the function that we were performing the Newton method bisection to find the x-intersect. We did that by passing that f function into the function itself, if you recall. So, map functions are extremely useful, as I'm sure you're finding out in Python. So, yeah. Any questions about that? Good. So, yes. One more point. So, in Haskell, have they talked about lambdas yet? Okay. Good. Python also supports lambdas. In a sense, obviously, Python lambdas are, they're lambdas in Python are the 7-year-old wearing the the high heels and the lipstick of the mother pretending to go to work, but, you know, it is what it is. Okay, I'll stop being mean to Python. So the syntax for a lambda in Python, you specify your variable names up front, you then have a colon and the expression from which you wish to perform argument extraction. So, you know, basically, if you take away the fact that this should be in parentheses, take away the slash in front, and replace the colon for an arrow, you're basically in exactly the same territory you would be with a Haskell lambda, minus, of course, the fact that application of arguments to this follows Python convention as well, so it's not like you can just hit space and add arguments to it. You have to, you know, call arguments with the parentheses and the commas and, you know, the regular syntax for that, right? How much have they talked about lambda calculus in 1JC3? A little bit? Yeah. Enough? Yeah. Not nearly enough, in my opinion. Ouch. Did you know that lambda calculus is Turing complete? Yeah. Do you know how it's Turing complete? It's kind of cool. You guys want like a 3-minute digression on why lambda calculus is Turing complete? So, what do you need for Turing completeness? The ability to generate an infinite program. Yes, question?
It has to be solved in every which way possible.
It has to be solved every which way possible?
Yes.
To be Turing complete?
Yes.
That's not exactly a formal mathematical definition, though.
It works.
Moving on. So, in lambda calculus, it is actually possible to derive true and false values. It's kind of interesting. I'm going to just bring up some slides briefly from a third-year course, if you don't mind, because it's just in the slides, right? This may be of slight interest to some. Hopefully this is of some interest to people. Hopefully you didn't take this degree program to not be interested in lambda calculus. But, so, under lambda calculus, right, you can define true and false values as functions. True is a value which takes two arguments and returns the first one, and false takes two and returns the second one. So, using that, you can define a bunch of like you can define all of your regular Boolean operations, like and takes two, you know, truth values, ideally, and applies false to C and C to B, and that actually works. If you call this and on true into true, you can actually derive it down through function applications. True and true is true, right? False, true and false is false, if you go through derivations. But that doesn't answer, so we can do Boolean algebra inside of lambda calculus. We can also do numeric algebra using church numerals. So basically this looks like quite a lot like piano or arithmetic. Have you guys taken piano or arithmetic? A little bit? So basically all natural numbers can be defined in terms of 0 and some number of applications of a successor function, right? So if you define your numerals in this manner, you can actually, you see, you know, 3 is S applied to Z with both S and Z extracted as arguments, right? And you can do math this way. So, fine. Still doesn't answer the question, why is this Turing complete? Although, the definitions of the Booleans do yield quite easily a like the definitions of true and false themselves encode if statements, which is kind of cool, right? So if you take an if statement, you must have both branches defined. If you apply the two branches to true, then you get the true branch of the if statement. If you apply those two branches to false, you get the false branch of the if statement. So the definitions of true and false themselves encode if statements in lambda calculus, which is kind of cool. Kind of a cool result. But again, that does not solve the problem of why it's Turing complete. And the answer is, you have such things as the omega function. So the omega function is a function that when you apply, when you try to compute this, you get back the same result. Like you get this expression back, right? So lambda x of x applied to x, and you apply to that lambda x of x applied to x, right? That just applies this guy to itself twice because this guy is the same as that guy. Evaluating this expression yields the same expression again. This is what you might call an infinite recursion as expressed in lambda calculus. This is a little bit more. This is a little bit different from general recursion, which requires what's called the Y combinator or the fixed point combinator. But that's why lambda calculus can be used to compute anything. It's a little bit complicated, but I think a very interesting mathematical subject, which I'm sure you'll cover in detail in later courses. Yes?
I don't fully understand what it means to be Turing complete.
You don't? Okay. All right. So Turing completeness then. All right. I'll make this a slightly brief digression. So Alan Turing, right? Grandfather of computation, right? He came up with a model of computation known as the Turing machine. You've heard of it? Yeah. So you have a strip of tape, you have a head that can read values, write values, jump around the tape, move around the tape. This is a Turing machine, right? One of the very, very famous results that Alan Turing came to very early in his career as an academic was what is known as the Church-Turing thesis. So lambda calculus was invented by another Brit by the name of Alonzo Church. Alonzo Church was Alan Turing's PhD supervisor, right? And together, they came up with the Church-Turing thesis, where Alonzo Church had lambda calculus, which was his model of computation. Turing had the Turing machine, which is his model of computation. The Church-Turing thesis demonstrates the equivalency in terms of computable things between those two systems, right? So, what it means to be Turing complete, sometimes the term Turing equivalent is used to mean Turing complete. What it means is, for a system of computation to be Turing complete, it means that system of computation is ultimately expressible in terms of a Turing machine. It can be written as a Turing machine, right? It might be a very long, complicated Turing machine, but a Turing machine nonetheless. And you have this very interesting result, right, where essentially all forms of computation, like the maximal level of computation that any mathematical computing system has achieved so far in human history has been demonstrated to be Turing complete, right? So if you take, for example, Markov chains, which is another alternative way of computing things, also fundamentally expressible as a Turing machine. right? So, when we say that a programming language is Turing complete, what we mean is, of course, if we wanted to, we could express this as a Turing machine, which is a kind of, from a pragmatic standpoint, means any program which you can write in that system can be written in any other computational system, right? Now, and vice versa. The vice versa is very important, right? So there are some programming languages which are not Turing complete, right? If you guys have occasion to take any of Dr. Call's grad level courses, he talks about a language called AGDA, which is essentially formal Haskell with dependently typed Haskell. So it's like Haskell, but it has even more math somehow. And AGDA is a very interesting language because it is impossible to compile AGDA unless you have not only created the program, but at the same time created a proof of correctness for the program. So it cannot compile programs which are not formally proven, like mathematical formal proof of correctness must accompany that to be compiled. So, you know, kind of interesting with respect to that. However, not Turing complete. AGDA is not Turing complete. Haskell achieves Turing completeness by allowing theoretically infinite data structures and not really having to deal with them by using lazy evaluation, right? AGDA does not support infinite data structures because you can't prove the correctness of something happening over an infinite data structure. So it does not meet the criteria for Turing completeness. That's not to say it isn't a useful language, but there are certainly Haskell programs you can write that are not expressible in AGDA. Does that make sense? Thank you for the question. Any other questions? Any other theory of computation questions? Okay, this is different from the Turing test. Does anybody know what the Turing test is? Yes?
Is this the one where it tests, never mind.
Yeah.
I think it was that.
Yes?
I believe it looks like if a computer can make you think that it's a human, it is a human?
Yes. Well, it's a test for basically it's like a test of have we achieved like general artificial intelligence, right? So if you're like typing on a computer and communicating with some entity, if it's a program but it manages to fool you into thinking that it's not a program, then that's a good test to see whether it's achieved general intelligence. So yeah, there's another one, like the Chinese room experiment, which is another interesting one if you want to look up these types of tests of AI. I forget how the Chinese room experiment works exactly, but yes.
It's you have a room full of a bunch of Chinese to English translations, but people are like giving you things that you don't understand. Sorry, it doesn't translate it. You learn every possible response to every possible, I guess, input in Chinese, but you don't actually know Chinese.
Right. Yeah. Exactly. Anyway, just, we should get back on track. Computing is a very interesting field. The Chinese room experiment is a thought experiment, not a real experiment. They haven't actually done that. It also, of course, operates on the assumption that you don't know Chinese, and there are, I'm sure, plenty of people in the room who do. So I guess that makes you ineligible to perform the experiment. I'm not sure. You'd have to pick a different language. Anyway, so let's talk about numerical computations. likely to be everybody's least favorite topic. So we're going to take a journey now into some of the lower level details of how computers store numbers. When you hear this term numerical computation, what you should think of is we're talking about computer number theory. How does the computer store numbers? How does it retrieve numbers? What do numbers mean? What is a number? What is even anything? As I'm sure everybody in this room is aware, computers store every single piece of information which they store in a series of ones and zeros held in various types of hardware memory, right? Therefore, because everything is in binary, everything is fundamentally reducible to numbers in a computer system. There's no concept of words. Even things that pretend to have a concept of words don't, like autocompletes. So, we're going to talk about the integers, then we're going to talk about floating point numbers, then we're going to talk about more algorithms, and then we're going to talk about why floating point is terrible. Or at the very least, it's good for what it does, but, you know, there are some fundamental problems with floats that we need to discuss, which I think I've already discussed with you guys. So let's talk about the integers. So, base 10 decimal representation. I'm hoping that this comes as no surprise to anybody, but this is how Arabic numerals work. You have place values. Each place value is multiplied by a subsequent power of 10, right? So the thousandth digit is multiplied by 10 to the 3, etc., etc. This is how numbers have worked, for a long time. Basically, this is better than Roman numerals because you can add columns, you know. But anyway, base 2 representation. It's technically binary, not decimal, but so this is how numbers work inside of your computer, right? The computer is only able to express zeros and ones. There's no gray area, right? It's either a 0 or it's a 1. Because, the decimal digits run from 0 to 9, which is 1 less than the base of the system, right? So, if you are only able to express 0 and 1, that means that necessarily the base of your system must be 1 higher than 1, which is 2, right? So, that's why everything's based on the number 2. So, this number is 1 times 2 to the power of 0 plus 1 times 2 to the power of 3 plus 1 times 2 to the power, 2 to the power of 2, 2 to the power of 3, etc., etc. That's 8 plus 4 plus 1, yielding 13. If you're in computer science long enough, you get pretty good at rattling off the base 2 exponents. So, what is the decimal base 10 representation of the following binary base 2 number? I'll give you guys a moment to calculate that out. Oh, wait, give it away. How many people think 11? How many people think 27? How many people think 54? 59? How many people would rather not be here right now? There we go. The answer is, of course, 27. It's 1, 2, skip the 4, 8, and 16, right? So, your basic approach, of course, to converting from the binary system into decimal is to simply take all of the bit values that compose the number, multiply them by their respective powers of 2, take the sum of all of those, and that yields your number, right? It's like, okay, sure. Incidentally, the way that Python chooses to do things is a little bit dumb, but it is possible in Python to convert numbers into binary. So if we take, for example, 27, convert to binary. Now I'd just like you to pay attention to what the output of this function was. That is a string, my friends. So the output of the binary function is to display it as a string. Also, very, very important, the 0b here, that's not part of the number. That's an indication that the number is a binary number, right? This is actually the same, many, many C-based languages use this convention for being able to write numbers in other bases. So, for example, if you want to write this number, if you want to write a binary number and have it interpreted as a regular integer and not as a string, if you write a literal composed of binary digits and put 0b in front of it, it will interpret that as binary digits that you're composing into an integer, and it'll just print that out. Make sense? Question?
So do we have to put 0b every single time whenever we want to convert binary to the decimal?
Yes. Yeah. The 0b designates this literal as being expressed using binary digits. Make sense? Question?
Is there any decimal or hexadecimal type of thing?
Hexadecimal. Yeah. Hexadecimal is X. Octal is O. And I think decimal, I don't know if this actually works. No. Decimal just has no tag. Yeah, by default. We'll talk about octal and hexadecimal. Ray at the back, do you have a question?
Yeah, can't you also convert a binary into an integer using the int function? The binary thing and then have a comma too?
Yes, but it's useful to know how to do this for every other language. But yeah, if you have this the string, you can also use int. Specifying base 2. There we go. You can do it that way too. There's a way of reading in these strings. It's still kind of dumb that it does it with strings, but it is what it is. So, fine, good. Well, if this were expressed as a summation, this would be the summation. You guys have seen summation notation in math before, I assume. No? No, are you kidding? Okay. Quickly, very quickly, this is, you repeat this term with I being from I being at the bottom, like this value instantiated, and then go to the value at the top. This is what a while loop looks like in a mathematical formula. All right? So, good. If we were to express this as a Python program, it is thus. Starting at the leftmost digit, the accumulator is multiplied by the base and the next digit is added. This is Horner's rule. So if you don't want to do multiplication by 2 to the power of this big long thing, then it is possible to simply continuously multiply, basically you can factor out the powers of 2 as you go along, and that prevents you, that means you don't need to use the power function on big powers, because the power function, in earlier computer iterations required floating point libraries, and it's just a little bit strange, so you can not do that if you want. It's not really an important point. All right. Going the other way, the thing that we want to do to convert from decimal to binary, we wish to extract out all of the digits composing a number, right? So this requires repeated performance of the modulus operation with the base that you're looking for, followed by integer division by the base that you're looking for. You follow that down, collect up the ones, and that is your binary number. Make sense? Have I lost anybody? No? We're good? Question? You had your hand up? No? Okay. All right. Good. So, skip, don't care. So, a lot of time, a lot of things covered. If you were to express this as a function, it would look something like this. Notice that this is again building up a string rather than some kind of native representation. So, and then decimal to binary, again, the other way around. This is actually adding, this is without the explicit 1 and 0 literals. We can actually achieve those literals by performing string conversion on the results of the modulus operation. So you can take that out and save yourself an if statement, but so it goes. Any questions? Okay. Oh, was there a question? Now we come to an interesting question. The negative integers are not addressed in the slides, but I can give you the rundown, I think, in the time we have remaining in class. It's very useful and interesting to know. So, the question we may have, how does one represent negative numbers inside of a computer system? Well, let's see what happens when we binary convert something that's negative. Ha! Python, you bitch.
Yeah.
Look at... Come on! What the hell is that? All right. Okay. I apologize for that the explicit content. Oh, but that's not even true. Oh, I hate Python so much. All right. So, let's imagine that we wanted to represent numbers that can be negative inside of our binary system. The most straightforward and intuitive way of doing this would be to put on the front of the number a single bit which designates whether or not it's negative, right? Simple, right? So, if we had a number like, if we had a number like 5, 101, positive, negative, or positive, or just having a 0 there would be 5, and 101 would be negative 5, right? So this is known as sign magnitude notation. I'm doing this in this because I don't have a frigging chalkboard. So, sign magnitude, right? Sign magnitude has a few problems. Number one, we might expect in sign magnitude, we want numbers to work properly. Like, we don't want to have to do anything special to add a 1 or a 0 with sign magnitude notation, right? So, for example, if we had 1101, which is negative 5 in sign magnitude, and we wanted to add to it 0001, which is positive 1, what is the correct result? Negative 4. What do we get when we actually perform the addition? We get 1110. right? Two ones add to 0 and carry a 1 to the next place value, and then it's just like regular addition, but as applied to binary numbers, right? So what is that? Well, it's got a negative sign bit, good so far. However, we've got 2 plus 4, which is equal to 6. So, sign magnitude doesn't work on arithmetic. You have a further problem with sign magnitude, which is that it has 2 zeros, right? You have both a positive and a negative 0. In general, when you have a new number system, it's not a good idea to have both a positive and a negative 0, because anytime you want to compare something to 0, you have to compare it to either positive or negative 0, and that's just like, that's hardware hell for a hardware designer, right? So sign magnitude is not what we want to do, right? So the question then becomes, how do we get the math to line up, right? So we then go to a form known as 1's complement, right? Negative numbers might be expressed by simply inverting all of the bits, leaving the sign bit, right, but inverting all of the rest of the bits. So, if we, right, let's, I'll use a slightly different one this time. So, this is 1's complement. Let's say we wanted to do 7 minus 3, or 7 plus minus 3, right? We should get 4, right? So 7 is 0, 1, 1, 1. That's 7. And what would 4 be if we took all of the, or negative 3? What would we have if we reversed all the bits? So 3 is 0, 0, 1, 1. So if we took 1's complement of that, we get 1, 1, 0, 0, right? So that is our representation of negative 3 in 1's complement, right? So what do we get if we add these? We get, starting from the back, we get 1, 1, 0, carry the 1, 0, and then we have a bit that gets thrown off, right? So, in this way, right, what's 0, 0, 1, 1? It's 3. So this is incorrect, right? But it's a lot closer to correct. It's actually only off by 1. It turns out, if you add one more rule, that if the last digit generates a carry, you take that carry and you add it around to the other side, then this suddenly works. So because we generated a carry bit, we add one more to it, and that yields the following. Suddenly we get the correct answer, right? So that's 1's complement. Okay, sure, but we still have the problem of 2 representations of 0. Because if we have 0, which is just 0, 0, 0, 0, and we apply a negative to it, we get 1, 1, 1, 1. Right? So we've still got 2 representations of 0. So, the actual representation of negative numbers that are used inside of computer systems is what's called 2's complement. So, it is not sufficient that we simply invert the bits. We do invert the bits to negate an integer, but then, once we're finished with that, we also add 1 to that integer. All right? So, under 2's complement, right, let's do the same math. 0, 1, 1, 1 is 7. We want to come up with a representation of -3. So we start off with 3. We invert all the bits. And then we add 1 to it, right? This will be our 2's complement representation of -3. Now what happens if we add these numbers together? We get 0, carry the 1, 0, carry the 1, 1, carry the 1, 0 with a carry. All right? And that is, of course, 4. Right? Now, here's an interesting thing. What happens to our 0? Right? Let's see what happens when we try to take -0. Right? So 0 is all zeros, obviously. We invert all of those, and then we add 0, or we add 1 to that. Hopefully everybody can see that that will come out to the following, but this front digit is dropped, so we end up with taking the negation of 0, resulting in the same representation that we had before for 0. Make sense? So, basically, this means that the range that's expressible on a negative, so like if you were to do a number line of these guys, right? Let's do a very quick one. Let's do 3 digits, right? Right? That's 0, that's 1, that's 2, right? This is so that will be negative 1, right? That'll be -2, -3, and then -4. Am I getting the math right? Oh, I missed one. There we go. Thank you. Thank you, brain. So, the consequence of this is that the range of integers expressible using 2's complement arithmetic ranges from -2 to the power of the number of digits you have to 1 minus that in the positive range. So basically, the 2 zeros have been eliminated, but the negative side has absorbed one of those 0 values and has become 1 longer. Does that make sense? Any questions? So yeah, that's how negative numbers are represented. Yeah, good. I think that's about as much damage as we can do today. See you next week.